My name is Professor Michio Kaku. I'm a professor of theoretical physics at the City University of New York, and I specialize in something called string theory. I'm a physicist, and some people ask me the question, what has physics done for me lately? I mean, do I get better color television? Do I get better internet reception with physics? And the answer is yes. You see, physics is at the very foundation of matter and energy. We physicists invented the laser beam. We invented the transistor. We helped to create the first computer. We helped to construct the internet. We wrote the World Wide Web. In addition, we also helped to invent television, radio, radar, microwaves, not to mention MRI scans, PET scans, X-rays. In other words, almost everything you see in your living room, almost everything you see in a modern hospital at some point or other can be traced to a physicist. Now, I got interested in physics when I was a child. When I was 8, a great scientist had just died. I still remember my elementary school teacher coming into the room and announcing that the greatest scientist of our era has just passed away. And that day, every newspaper published a picture of his desk, the desk of Albert Einstein. And the caption said, I'll never forget, the unfinished manuscript of the greatest work of the greatest scientist of our time. And I said to myself, why couldn't he finish it? I mean, what's so hard? It's a homework problem, right? Why didn't he ask his mother? Why can't he finish this problem? So, as a child of 8, I decided to find out what was this problem. Years later, I began to realize that it was the theory of everything, the unified field theory, an equation that would summarize all the physical forces in the universe, an equation like E equals mc squared. That equation is half an inch long, and that equation unlocks the secret of the stars. Why do the stars shine? Why does the galaxy light up? Why do we have energy on the earth? But then there was another thing that happened to me when I was around 8 years old. I got hooked on the Saturday morning TV shows, in particular, Flash Gordon. And I was hooked. I mean, every Saturday morning, watching programs about aliens from outer space, starships, ray guns, invisibility shields, cities in the sky. That was for me. But after a few years, I began to notice something. First of all, I began to notice that, well, I didn't have blonde hair and blue eyes. I didn't have muscles like Flash Gordon. But it was a scientist who made the series work. In particular, a physicist. He was the one who discovered the ray gun, the starships. He was the one who created the invisibility shield. And then I realized something else. If you want to understand the future, you have to understand physics. Physics is at the foundation of all the gadgetry, the wizardry, all the marvels of the technological age. All of it can be traced to the work of a physicist. Most of science fiction is, in fact, well within the laws of physics, but possible within maybe 100 years. And then we have impossibilities that may take 1,000 years or more. That includes time travel, warp drive, higher dimensions, portals through space and time, stargates, wormholes. You know, if you were to meet your great-grandparents of the year 1900, they were dirt farmers back then. They didn't live much beyond the age of 40 on average. Long-distance communication in the year 1900 was yelling at your neighbor. And yet, if they could see you now with iPads and iPods and satellites and GPS and laser beams, how would they view you? They would view you as a wizard or sorcerer. However, if we can now meet our grandkids of the year 2100, how would we view them? We would view them as gods, like in Greek mythology. Zeus could control objects around him by pure thought, materialize objects just by thinking. And their perks being a Greek god, Venus had a perfect body, a timeless body, and we are beginning now to unravel the genetics at the molecular level of the aging process. And then Apollo, he had a chariot that he could ride across the heavens. We will finally have that flying car that we've always wanted to have in our garage. By the year 2100, we will have the power of the gods. To paraphrase Arthur C. Clarke, any sufficiently advanced technology is indistinguishable from divinity. So let's now begin our story. The history of physics is the history of modern civilization. Before Isaac Newton, before Galileo, we were shrouded with the mysteries of superstition. People believed in all sorts of different kinds of spirits and demons. What made the planets move? Why do things interact with other things? It was a mystery. So back in the Middle Ages, for example, people read the works of Aristotle. And Aristotle asked the question, why do objects move toward the earth? And that's because, he said, objects yearn to be united with the earth. And why do objects slow down when you put them in motion? Objects in motion slow down because they get tired. These are the works of Aristotle, which held sway for almost 2,000 years until the beginning of modern physics with Galileo and Isaac Newton. When the ancients looked at the sky was full of mystery and wonder. And in the year 1066, the most important date on the British calendar, there was a comet which sailed over the battlefield of Hastings. It frightened the troops of King Harold, and a young man from Normandy swept into England and defeated King Harold at the Battle of Hastings, creating the modern British monarchy. But the question is, where did the comet come from? What was this comet that mysteriously paved the way for the coming of the British monarchy? Well, believe it or not, that same comet, the very same comet that initiated the British monarchy, sailed over London once again in 1682. This time, everyone was asking the question, where do comets come from? Do they signal the death of the king? Why do we have messengers from the heavens in the sky? Well, one man dared to penetrate the secrets of comets, and that was Isaac Newton. In fact, when Isaac Newton was only 23 years old, he stumbled upon the universal force of gravitation. According to one story, he was walking on his estate in Woolsthorpe, and he saw an apple fall. And then Isaac Newton saw the moon. And then he asked the key question which helped to unlock the heavens. If apples fall, does the moon also fall? And the answer was yes. And that answer overturned thousands of years of mystery and speculation about the motions of the heavens. The moon is in free fall. Just like an apple, the moon is constantly falling toward the earth. It doesn't hit the earth because it spins around the earth and the earth is round, but it's acting under a force of gravity. So Newton immediately tried to work out the mathematics, and he realized that the mathematics of the 1600s was not sufficient to work out the motion of a falling moon. So what did Isaac Newton do? When he was 23 years old, not only did he stumble upon the force of gravity, but he also created calculus. In fact, he created calculus at the rate at which you learn it when you're a freshman in college. And why did he create calculus? To calculate the motion of a falling moon. The mathematics of his age was incapable of calculating the trajectories of objects moving under an inverse square force field. And that's what Isaac Newton did. He worked out the motion of the moon. And then he realized that if he understands the moon, he also understands the motion of the planets in the solar system. And Isaac Newton invented a new telescope. It was the reflecting telescope, and he was tracking the motion of this comet. Well, it turns out that everyone was talking about the comet, including a rather wealthy Englishman by the name of Edmund Halley. So Edmund Halley, being a wealthy merchant, decided to make a trip to Cambridge to talk to England's illustrious scientist, Sir Isaac Newton. Well, Edmund Halley asked Newton, "What do you make of this comet?" No one understands comets. They're a mystery. They've been fascinating people for centuries, for millennia. What are your thoughts? And then, I paraphrase, but Isaac Newton said something like this. He said, "Oh, that's easy. That comet is moving in a perfect ellipse. It's moving in an inverse square force field. I've been tracking it every day with my reflecting telescope, and the path of that comet conforms to my mathematics exactly." And of course, we don't know what Edmund Halley's reaction was, but I paraphrase. He must have said something like this: "For God's sake, man, why don't you publish the greatest work in all of scientific history? If correct, you have decoded the secret of the stars, the secret of the heavens. Nobody understands where comets come from." And then Newton responded and said, "Oh, well, it costs too much. I mean, I'm not a wealthy man. It would cost too much to summarize this calculus that I've invented and to work out all the motion of the stars." And then Halley must have said this: "Mr. Newton, I am a wealthy man. I have made my fortune in commerce. I will pay for the publication of the greatest scientific work in any language." And it was Principia. The principles, the mathematical principles that guide the heavens. Believe it or not, this is perhaps one of the most important works ever written by a human being in the 100,000 years since we evolved from Africa. Realize that this book sets into motion a physics of the universe. Forces that control the motion of the planets. Forces which can be calculated. Forces which govern the motion of cannonballs, rockets, pebbles. Everything that moves according to the laws of motion and the calculus of Sir Isaac Newton. In fact, even today, when we launch our space probes, we don't use Einstein's equations. They only apply when you get near the speed of light or near a black hole. We use Newton's laws of gravity. They are so precise that when we shoot a space probe right past the rings of Saturn, we use exactly the same equations that Isaac Newton unraveled in the 1600s. That's why we've been able to unravel the secrets of the solar system, complements of the laws of motion of Isaac Newton. So what Newton did was not only did he set into motion the ability to calculate planets, he also set into motion a mechanics. Machines now operated upon well-defined laws. Newton's 3 laws of motion. The first law of motion says that objects in motion stay in motion forever unless acted on by an outside force. You see that in an ice skating rink. You shoot a puck and it goes all the way down forever unless acted on by an outside force. That's different from Aristotle's law of motion. Aristotle said objects in motion eventually stop because they get tired. The second law of motion says force is mass times acceleration, and that equation made possible the Industrial Revolution. Steam engines, locomotives, factories, machines, all of it due to the mechanics set into motion by Isaac Newton's second law of motion, force is equal to mass times acceleration. And then Newton had a third law of motion. For every action, there's an equal and opposite reaction. That's the law of rockets. That's why we have rockets that can sail into outer space. So the lesson here is, when scientists unraveled the first force of the universe, gravity, that set into motion the Industrial Revolution. A revolution which toppled the kings and queens of Europe, which displaced feudalism, ushering in the modern age, all because a 23-year-old gentleman looked up and asked the question, does the moon also fall? You know, when I was a kid growing up in California, I would see pictures of the Empire State Building. And I said to myself, how could they possibly build such a big building and not know that it's going to fall? Why doesn't it fall? They didn't build scale models of the thing. You couldn't have an Empire State Building that big to test whether it's going to fall or not. How did they know ahead of time that that building wouldn't fall? And the answer is Newton's laws of motion. In fact, today I teach Newton's laws of motion, and you can actually calculate the forces on every single brick of the Empire State Building. Using Newton's second law of motion, force is mass times acceleration. When Newton unraveled the force of gravity, that was the first force. Now let's take a look at the second force, an even greater force which has touched all of our lives, and that is the electromagnetic force. Ever since humans saw lightning bolts light up the sky, ever since they were terrified by the sound of thunder, they've been asking, do the gods propel lightning bolts and create thunder? Are they angry at us? Scientists begin to realize that the lightning bolts and the thunder can be duplicated on the Earth, that we can actually create mini lightning bolts using electricity. But it wasn't until the 1800s that finally we began to unlock the second great force which rules the universe, the electromagnetic force. Michael Faraday would give Christmas lectures in London, fascinating everyone from adults to children. And he would demonstrate the incredible properties of electricity. Some people, for example, ask a simple question. If you're in a car or an airplane and you get hit by a lightning bolt, why don't you all get electrocuted? Why don't you all die? Well, Faraday answered the question. He would create a cage. He would walk into this steel cage, electrify it, and he wouldn't get electrocuted at all. That's called the Faraday cage. And every time you walk into a metal structure, you get shielded by this metal object. Well, what Michael Faraday did was he helped to unleash the second great revolution with something called Faraday's law. A moving wire in a magnetic field has its electrons pushed, creating an electrical current. That simple idea unleashed the electric revolution. And that's why we have hydroelectric generators, dams that can produce enormous amounts of power. That's why people build nuclear power plants. That's why we have electricity in this room right now. On a very small scale, you use that in your bicycle. When you put a bicycle lamp on your bicycle, the turning of the wheel spins a magnet. The magnet then pushes electrons in a wire, and that's why electricity lights up in your bicycle lamp. So in other words, electricity and magnetism were unified into a single force. We once thought that electricity and magnetism were separate. Now we know they are, in fact, the same force. So if a moving magnet can create an electric field, this means that a moving electric field can create a magnetic field. But if they can create each other, why can't they oscillate and create a wave? So that moving electric fields create magnetic fields, create electric fields, create magnetic fields, infinitum, to create a wave. Well, around the time of the American Civil War, a mathematical physicist, James Clerk Maxwell, calculated, using the work of Faraday, the velocity of this wave. In one of the greatest breakthroughs of all time, James Clerk Maxwell calculated the velocity of this wave and found out it was the velocity of light. And then he made this incredible discovery. This is light. That's what light is. It doesn't by accident travel at the speed of electricity. It is light itself. And the equations were written down by James Clerk Maxwell. Unfortunately, Michael Faraday himself did not have a formal education. He could not put into mathematical form his own work. James Clerk Maxwell was a theoretical physicist, just like myself. He wrote down the mathematical physics of oscillating electric fields and magnetic fields, and they are called Maxwell's equations. These equations have to be memorized by every physicist in grad school. You cannot get your PhD without memorizing these equations. Every engineer who deals with radar and radio has to memorize these equations. And so, if you go to Berkeley, where I got my PhD, you can buy a t-shirt which says, "In the beginning, God said, the four-dimensional divergence of an antisymmetric second-rank tensor equals 0, and there was light." Ladies and gentlemen, this is the equation for light. The consequences of the electromagnetic revolution touch all of us. This is a picture of the Earth from outer space. Look at this picture. Europe, electrified. You can actually see the fruits of all of our efforts to create electricity, to energize our lives in one picture, seeing the Earth from outer space. So let's now talk about how Faraday and Maxwell's work touches your life as well. This is the Internet. The Internet is a simple byproduct of the electromagnetic force, and you can see that where there is the Internet, there's prosperity. There's science. There's entertainment. There's economic activity. Where there's no Internet, there's poverty. And in the future, the Internet will be miniaturized and it'll be placed in your glasses. Your glasses will recognize people's faces and display their biography next to the image as you talk to them. And then when they speak Chinese to you, your glasses will translate Chinese into English and print out subtitles right beneath their image. So in the future, you will know exactly who you are talking to without even talking to them. And this means that at a cocktail party, if you're looking for a job, but you don't know who the heavy hitters are, in the future, you will know exactly who to suck up to. In the future, chips will only cost a penny because we can manufacture tinier and tinier transistors. You will have Faraday's electromagnetic force inside your body. This is a pill. It has a chip in it. The chip is smaller than an aspirin pill. It also has a TV camera and a magnet. When you swallow it, the magnet guides the camera, taking pictures of your stomach, your intestines, because we all know what middle-aged men fear the most, colonoscopies. And this gives new meaning for the expression, Intel inside. Now, let's talk about the next great forces which rule the universe. We talked about gravity, which allows us to calculate the motion of the planets. The mechanics created by Newton helped to unleash the Industrial Revolution. Michael Faraday worked out the electromagnetic force, which gave us the wonders of the electric age. And now let's talk about the nuclear age, the stars and the sun. People have been fascinated by the sun. Apollo was the god that strode across the heavens in his fiery chariot. But hey, when you calculate how long coal or oil will burn like the sun, you realize that in just a few hundred years, the sun would burn to a crisp. So what could possibly last for billions of years? There must be a new force, a nuclear force. Einstein and others helped to unravel the secret of the stars. The nuclear force comes in two types, weak and strong. The weak nuclear force governs radioactive decay. The strong nuclear force is one of the strongest forces in the entire universe. It's so strong, it holds our protons together ever since Genesis, the beginning of time. The equation which allows for the liberation of energy is Einstein's famous equation, E equals mc squared. What Einstein showed was that the faster you move, the heavier you get. So your weight is not a constant. When you move very rapidly, you get heavier, something which we measure every day in the laboratory. Now this means that the energy of motion transformed into mass, because you get heavier. Now listen carefully. The faster you move, the heavier you get, which means the energy of motion, E, turns into m, your mass. And the relationship between E and M is very simple. It takes 1 second to write it down on a sheet of paper. It is exactly E equals mc squared. So the nuclear force helped to explain the secret of the sun. But it also created a Pandora's box. Because inside the nucleus of the atom are particles. And when you smash these particles, what do you get? More particles. And when you smash them, what do you get? More particles. In fact, we are drowning in subatomic particles. Hundreds, thousands of subatomic particles every time we smash atoms. Now, we smash atoms using something called atom smashers or particle accelerators. I built my own particle accelerator when I was in high school. When I was in high school, I went to my mom one day, and I said, "Mom, can I have permission to build a 2.3 million electron volt betatron particle accelerator in the garage?" And my mom said, "Sure, why not? And don't forget to take out the garbage." So I went to Westinghouse, and as a high school kid, I asked for 400 pounds of transformer steel. I asked for 22 miles of copper wire, because I wanted to create a 6 kilowatt, 10,000 Gauss magnetic field to energize my atom smasher. With 22 miles of copper wire, how could you wind it? We did it on the high school football field. I put 22 miles of copper wire on the goalpost, gave it to my mother. She ran to the 50-yard line, unraveling the spool of wire. She gave it to my father, who then ran to the goalpost, and we wound 22 miles of copper wire on the high school football field. Well, finally, my atom smasher was ready. It consumed 6 kilowatts of power. That's every single ounce of power that my house could deliver. I plugged my ears, I closed my eyes, I turned on the power, and I heard this huge crackling sound as 6 kilowatts of power surged through my capacitor bank. And then I heard a pop, pop, pop sound as I blew out every single circuit breaker in the house. The whole house was plunged in darkness. My poor mom, every time she'd come home, she would see the lights flicker and die. And she must have wondered, why couldn't I have a son who plays baseball? Why can't he learn basketball? And for God's sake, why can't he find a nice Japanese girl? I mean, why does he have to build these machines in the garage? Well, these machines that I built in my garage earned the attention of a physicist, Edward Teller, father of the hydrogen bomb. And he arranged for me to get a scholarship to Harvard. And my career got a head start. He knew exactly what I was doing. I didn't have to explain to him that I was experimenting with antimatter. I was creating anti-electrons in my mom's garage and using atom smashers to eventually create beams of antimatter. Antimatter is the opposite of matter. It has the opposite charge. So an electron has negative charge. The positron, or anti-electron, has positive charge. This means that you can now create anti-molecules and anti-atoms. Anti-hydrogen was made at CERN, outside Geneva, Switzerland, and also at Fermilab outside Chicago, where I have anti-electrons circulating around anti-protons. And in Brookhaven National Laboratory in Long Island, just recently, they detected anti-helium. We have 2 antiprotons with 2 antineutrons to create anti-helium. For every piece of matter, there's a counterpart which is made out of antimatter. And when the two collide, by the way, it releases the greatest energy source in the universe. It is 100% conversion of matter to energy by Einstein's equations, E equals mc squared. Inside the nucleus of the atom, we have particles upon particles when you smash them apart. In the 1950s, we were drowning in subatomic particles. In fact, J. Robert Oppenheimer, the father of the atomic bomb, once made a statement. He declared that the Nobel Prize in physics should go to the physicist who does not discover a new particle this year. That's how many particles were being discovered. So let's talk about the particle zoo. Right now, we physicists have unlocked hundreds, thousands of subatomic particles. And we've been able to piece them together into a jigsaw puzzle. It's called the Standard Model. It has 36 quarks, 19 free parameters, 3 generations of quarks, No rhyme, no reason, but this is the most fundamental basis of reality that we physicists have been able to construct. Billions of dollars, 20 Nobel Prizes have gone into the creation of the Standard Model, and it is the ugliest theory known to science, but it works. There's one piece missing, and that one piece that's missing is called the Higgs boson. We expect to find it. We want to create a higher version of this theory. And that theory, we think, is string theory. String theory is based on the simple idea that all the four forces of the universe, gravity, the electromagnetic force, and the two nuclear forces, can be viewed as music. Music of tiny little rubber bands. So if I had a super microscope and I could look right into the heart of an electron, what would I see? I would see a vibrating rubber band. And if I twang it, it turns into a neutrino. I twang it again, it turns into a quark. I twang it again, it turns into a Yang-Mills particle. In fact, if I twang it enough times, I get thousands of subatomic particles that have been cataloged patiently by physicists. String theory, we think, is a theory of everything. Now, string theory, in turn, can be summarized in an equation about an inch long. That's my equation. This is called string field theory. And how will we test it? We are building a machine, the biggest machine of science ever built in the history of the human race, outside Geneva, Switzerland. It is the Large Hadron Collider. So the Higgs boson, we think, will be created by the Large Hadron Collider. A tube 17 miles in circumference with two beams of protons circulating in opposite directions, then slamming together, creating a shower of particles. And among these particles, we hope to find the Higgs boson. But not only that, we hope to find particles even beyond the Higgs boson. The next set of particles beyond the Higgs boson are sparticles. The next layer of the jigsaw puzzle are called sparticles, superparticles, nothing but higher vibrations, higher musical notes of a vibrating string. And what else could we do? We can also unlock the secrets of the Big Bang. You see, Einstein's equations break down at the instant of the Big Bang and the center of a black hole. The two most interesting places in the universe are beyond our reach using Einstein's equations. We need a higher theory, and that's where string theory comes in. String theory takes you before the Big Bang, before Genesis itself. And what does string theory say? It says that there is a multiverse of universes. Where did the Big Bang come from? Well, Einstein's equations give us this compelling picture that we are like insects on a soap bubble, a gigantic soap bubble which is expanding, and we are trapped like flies on flypaper. We can't escape the soap bubble, and that's called the Big Bang theory. String theory says there should be other bubbles out there in a multiverse of bubbles. When two universes collide, it can form another universe. When a universe splits in half, it can create two universes, and that, we think, is the Big Bang. The Big Bang is caused either by the collision of universes or by the fissioning of universes. If there are other dimensions, if there are other universes, can we go between universes? Well, that, of course, is very hard. However, Alice in Wonderland gives us a possibility that maybe one day we might create a wormhole between universes. This is a wormhole. Think of taking a sheet of paper and putting two dots on it. The shortest distance between 2 points is a straight line. But if I can fold that sheet of paper, then perhaps I can create a shortcut through space and time, called a wormhole. This is a genuine solution of Einstein's equations. We can actually see this in string theory. The question is, how practical is it to go through one of these things? We don't know. In fact, there's a debate among physicists today. Stephen Hawking, many physicists are jumping into the game of trying to figure out whether it's physically possible to go all the way through a wormhole. Because if you could, then you might be able to use this as a time machine. Since string theory is a theory of everything, it's also a theory of time. And time machines are allowed in Einstein's equations, but to build one is extremely difficult. Far more energy is required than a simple DeLorean with plutonium. You know, trillions of years from now, the universe is going to get awfully cold. We think the universe is headed for a big freeze. All the stars will blink out. Stars will cease to twinkle. The universe will be so big, it'll be very cold. At that point, all intelligent life in the universe must die. The laws of physics are a death warrant to all intelligent life. There's only one way to escape the death of the universe, and that is leave the universe. We are now, of course, entering the realm of science fiction, but at least we now have equations, the equations of string theory, which will allow us to calculate if it is possible to go through a wormhole, to go to another universe where it's warmer, and perhaps we can start all over again. If you were to summarize the march of physics over the last 10,000 years, it would be the distillation of the laws of nature into four fundamental forces: gravity, electricity, and magnetism, and the two nuclear forces. But then the question is there a fifth force? A force beyond the forces that we can measure in the laboratory? And believe it or not, there are physicists who've actually looked very carefully for a fifth force. Some people think maybe it's psychic phenomena. Maybe it's telepathy. Maybe it's something called psi power. Maybe it's the power of the mind. Maybe consciousness. Well, I'm a physicist. We believe in testing theories to make sure that they are falsifiable and reproducible. We want to make sure that on demand, your theory works every single time without exception. And if your theory fails one time, it's wrong. In other words, Einstein's theory has to work every single time without exception. One time, Einstein's theory is proven to be wrong, the whole theory is wrong. Well, so far, we can reproduce these four physical theories, but a fifth theory cannot be reproduced. We've looked for it. Some people think that maybe a fifth force may be short range, like not over the nucleus of the atom, but ranging over several feet. And we can't find any. We physicists in the last 10 years have discovered a new energy source larger than the galaxy itself. Dark energy. Realize that in our universe today, 73% of our universe, the matter and energy, 73% is in the form of dark energy. The energy of nothing. That's what's blowing the galaxies farther and farther apart. That's the energy of the Big Bang itself. Kids ask the question, if the universe banged, then what made it bang? And the answer is dark energy. 73% of the universe's energy is dark energy. 23% is dark matter. Dark matter is invisible matter. If I held it in my hand, it would go right through my hand. It holds a galaxy together. 23% of the universe is dark matter. Stars, made out of hydrogen and helium, make up 4% of the universe. And then what about us? We, the higher elements, we made out of oxygen, carbon, nitrogen, tungsten, iron, we make up 0.03% of the universe. In other words, we are the exception. The universe is mainly made out of dark energy. The universe is mainly made out of dark matter, overwhelming the stars, overwhelming the galaxies, in fact. Now, what is dark matter, which makes up 23% of the universe? No one knows. String theory gives us a clue, but there's no definitive answer. So in other words, for you young aspiring physicists out there in the audience, you may be saying to yourself right now, why should I go into physics? Because you guys already have a candidate for the unified field theory, right? Just realize that every single physics textbook is wrong. Every single physics textbook on the earth says that the universe is mainly made out of atoms, right? There it is. The universe is mainly made out of atoms. Wrong. In the last 10 years, we have come to the realization that most of the universe is dark. And there's a whole shelf full of Nobel Prizes for the young people who can figure out the secret of dark matter and dark energy. Let me give some advice to you. If you are a young physicist, perhaps just getting out of high school, you have dreams of being Einstein, of dreams of working on string theory and stuff like that, and then you hit freshman physics. Let me be blunt. We physicists flunk most students taking elementary physics, and we're more or less encouraged to do so by the engineering department. We don't want to train engineers who make bridges that fall down. We don't want to create engineers that create skyscrapers that fall over. There's a bottom line. You have to know the laws of mechanics. So before you can work with the laws of Einstein, you have to work with the laws of friction, levers, pulleys, and gears. As a consequence, we have a very high flunk-out rate in elementary physics. So if you're a young physicist graduating from high school with stars in your eyes, and you encounter freshman physics for the first time, watch out. If you have a rough time, that's the way it is. I started out my life as an experimental physicist. Then I went to Harvard, and then I talked to my advisor, one of the world's greatest experimental physicists, Professor Pound, and he told me that maybe it's time to give it a rest. He said to me, your skills are much better suited to what you love the most, which is theory, mathematics, the world of higher dimensions. And I realized that he was probably right. The thing about physics, or even science, that really intrigues me the most is to find the most fundamental basis for everything. Rather than trying to massage a theory or make a theory prettier, why not find out why it works? What makes it tick? And that's what I do for a living. I'm a theoretical physicist. Thank you very much.